ठुकरा दिया था इस conclusion of having that we will not use T1 time for structural elucidation, although T1 is it is good enough to elucidate the structure, but right now the only purpose of T1 is to calculate T1 between different scales, right? 5 T1 time. Good, nice, high resolution NMR spectroscopy may आपको from one skein to the other skein you use a 5 T1 time delay. 5 T1 time because 5 T1 time is approximate time difference between the most efficient relaxing nuclei and time is a very safe time because within this particular time, you know, if it is 3 seconds, it means 15 seconds only. 15 seconds, you would be able to see everything relaxed back to the thermal equilibrium. This is the reason why you calculate T1 time, average T1 time. I just give you a figure that 5 T1 means that when you calculate a T1, 5 and you wait for that much time before you give a second pulse. When you start a second experiment, मैं समझता हूँ कि I think the intellectual power in this particular room is so tremendous that I'm overwhelmed. Right? Anyway, but let me. Okay, Maria, kindly use only positive signal and tell me the T1 time. So what she's actually saying is the following that in order to the full T1, see what is relaxation time? Relaxation time is the time to fully relax, right? And what is in case of a 180 X pulse, which bring your M naught to negative, positive Z is your T1, right? And in कैसे how you would calculate that? Then istikhara, can you do anything else? Can you do anything else to calculate T1 uh, for uh, for an experiment like this from Z? Remember, negative Z or positive Z longitudinal magnetization vector is non-observable, unobservable. It cannot be observed. It can only be observed by bringing it to, and that's what you are doing actually. Every time you're bringing it to the X5 plane, and one from the other experiment with only the time delay T1, right? These are the T1. Uh, I think yeah, Sarosh is Sarosh. Sarosh. Any I have a strong belief that from this particular room, there could be many interesting ideas come which spectroscopy and me. Okay. Any other idea? Detector is the accessibility. Sure. Uh, you know we can't do it, right? I want it to be crystal clear. I promise that I will teach you NMR spectroscopy for the rest of my life, whatever it is. Right? But I want it to become an absolute clear, crisp idea. Inversion recovery. And I'll be very happy if there is only one conclusion. I see a big question mark with the eyes and nose and ears. Any organic molecule which come along with a spectrometer, or you can do it on your sample too. Because 5T1 is good enough to afford problems. Okay? If you are giving only T1 time, one that you have to absolutely calculate T1 time so correctly that your magnetization vector after giving a 90 plus come on XY plane. Remember, if your magnetization vector has not really reached to the Z plus, anything which you give would bring it to the wrong place. So it is important that you absolutely thermal equilibrium, and you can do it with the standard samples which come with the NMR machine. There are sealed samples आते हैं, stable sealed samples जिनको लोग use करते हैं they use it for pulse calibration, for T1 calculation, for a number of other things also, and lots of these samples come. And you can use your own sample also by just giving it only two pulses, 180, a gap of your choice, and then 90x pulse. And then you see evolution of your NMR spectrum after a negative signal to fully positive signal. And this from fully negative to fully positive is your T1 time, right? You measure the T1 time, this process called inversion recovery method, because you fully invert your magnetization vector and then you let it recover and measure with different time interval. Thick? This is a good question actually. Generally, small molecular NMR spectroscopy, T1 is not very crucial. To be honest, you calculate T1 for any molecule which is in the range of 400 to 500. But if you have a very large molecule, then you need to calculate T1 in altogether different manner. Use the same process, but T1 can be very, very different. Very, very different. Different nuclei, and some of them are too slow to relax. I give you the example of carbon 13. Even in carbon 13, you have a problem. CH3 relax very quickly as compared to quaternary carbon, because quaternary carbon has no proton to give the energy to, right? Between T1 of a methyl and T1 of a quaternary carbon is tremendous, right? Therefore, you need to be careful that you have an average T1 and then multiply it with 5 to make sure that your poor quaternary carbon has also relaxed. And everything has reached to an absolutely thermal equilibrium. This is the purpose of T1 relegation. That's how you calculate and measure the spinniness. Other question? This is the range. Generally, the observation is that the fastest relaxing nuclei in a molecule and the slowest relaxing nuclei in a molecule generally have a difference of. That's why you don't want to give it a very long time. You can't have a 20 T1 time, because if you do that, then you waste lots of time between different scans. And you don't want to do that. You just want to give a sufficient time to ensure that everything is relaxed, and then you start another experiment in which you give another pulse and you bring it to the 98%. Remember, always remember that if there is an error in the initial position of the M naught, this error multiply with every pulse. Multiply with every pulse. Accumulate with every pulse. If magnetic is not on Z plus, it's on 10 degree. The 98 pulse will bring below the magnetization. 90 pulse will go somewhere else, you know. So multipulse experiments, the apply because of the wrong estimation of the original. Walaikum salam.
Sir, I am Aisha Nazi from Global University, Terrace Manfa. I have a question for you.
Please go ahead.
Sir, in the present slide, I'm not getting signals like you have written 3.4, 3.7. What are they?
These are relaxation time, T1. Relaxation time. 3.2, 3.4, 3.3, 4.8, 50, 3.2, 3.2, 3.7, 3.3. Accurate T1 time. Because remember, experiment multiple time, you don't see everything evolve at the same time. You need to have some more time before them are still not fully evolved. And then you calculate, so you can calculate the T1 time of each individually, observing that they have achieved a proper sensitivity integration which is supposed to have in a normal spectrum. So this first spectrum of yours should be a spectrum, a normal proton spectrum. And in between you see that some of them evolve fully, some of them are still evolving because of different T1 time. And therefore you calculate the T1 time for each one of them individually. But I said that this is not necessary. This was necessary, and this can still be very important. Use T1 time as your data to illustrate. I told you that there was an attempt and efforts in which people wanted to use T1 time for the calculation and elucidation of structure. For example, I say that the proton, I don't know what the chemical shift is, but let's assume that it's about 3.5 or something like this, that the protons which are oxy or alpha to NH generally have T1 at 5, right? And methyl T1 in the range of 3.3 to 3.2, right? So substantially different from each other. And you use these values to date the structure as you do for the frequency. You do the frequency exactly, you know that from 5 to 7 is olefinic region, from 6.5 to 8 region, you know, between 3 to 4.5 is alpha proton to hydroxy and NH. Negative point to 1 is a isopropyl protons, you know, from 1 to 2 or 1 to 1.5 is a methyl region, you know that from 1.5 to 2.5 or 3 is a multiple CH2 region. You know these values and you use to illustrate the structure. This is the same thing philosophy was sometimes put forward where people said use T1 time. And elucidate the structure, but this was generally accepted because of two reasons. One is that we were used to more conventional frequency NMR spectrum, and second was that required tables the required tables were available for frequencies before it, and they were aware of the fact that this methyl, O methyl, N methyl, S methyl would come these particular positions. People aromatic protons will come on this frequency position in Hertz. But the tables for T1 were not available, and therefore people decided not to use it. But it has a value, and this value is more practical nature of the problem. The practical is that in order to have a multi, you must really give them a time. You must really give them a time when they become absolutely relaxed. And why this is so? Because your detector, kindly remember, your detector cannot detect a full T1 time. Your detector can see your magnetization vector up to a certain tip angle. Then for detector it become invisible. But it has not really reached to the Z positive. Otherwise you could have done it much easier. So this T1 has a value. Okay. So that you can manipulate T1, would you be happy? No? If I tell you that I can relax quaternary carbon much faster than methyl, will you believe me? No, you won't believe me. I'm your teacher, you must believe me, right? Okay, anyway. There are relaxation reagents. There are certain metal complexes available. This is not to confuse you, just to tell you that people have done a lot of experiments to manipulate T1 also. You know, in compounds where quaternary carbon relax so slowly and thus have no signal at all, because if they can't relax, they can't have a signal, you know. And if they cannot give a signal, then you miss them out. So people use 0.05 millimolar europium. Europium is a metal, right? People do lots of, I used to do it, you know, this was my famous pastime, in which I used to add lots of relaxation reagent, in which I could see that the non-existing, not non-existing, but not appearing quaternary carbon start appearing, because I was able to make them relax by adding agent which help them to give energy. So you can play with it. Are you okay with T1? Or tea only? Tea, coffee? You see, for a particular type of nuclei, the difference between them is only because of the electronic involvement. No other factor. The factor would be involved chiromagnetic ratio when you compare carbon with the proton. But when you the proton or carbon with the carbon, it's only the electronic environment which make them resonate at a different chemical, right? Good question, thank you. Anything else? Seconds. Genuine time. That is the reason why we don't use T1. The relaxation time into frequency by using a mathematical calculation called Fourier. Anything else? Okay, let's move forward. Happy, see, मैंने यहाँ जान दी हुई है आप लोग खुशी. Tell me. Okay, let's move forward. Spin echo experiment. Is spin echo, right? Spin echo, spin inversion recovery is inversion recovery. It's not spin inversion recovery. Inversion recovery is spin inversion recovery. So spin echo experiment is very simple. Has lots of practical applications. experiment is a very simple experiment in which you give a 90x pulse, and when you give, always remember this magnetization vector all the time. Okay? You must understand that a 90x pulse means what? You know 90x pulse means xy plane. Where? On y, right? If you start detecting here, you don't need to worry about it. But here you are giving a delay because you want to do something interesting into it. When you give it a delay, something would happen. And the most obvious thing would happen would be that coherent signal, always remember coherent hota hai. First hota hai na, the first 90x pulse bring everything together at the same time, right, is a coherent signal. When you give them a time, they lose because of multiple reasons which I listed for you at the beginning. Let's assume that we are talking about two things. Number one is chemical shift. Okay, let's try to understand the chemical shift first. In between this time, this magnetization would split into many, as many as you have, right? Assume that you have only two different types of protons. Only two different types of proton. Okay, so this is one proton, this is the second type of proton. Now, question is that when one of them must be faster moving and the other would be slower moving. The slower moving doesn't really mean that it is really going to this direction. It means that it's just lagging behind. It's just lagging behind. I have two trains going with a differential speed. One is faster and the other is relatively slower. In reality, this backward with reference to you, and the faster is moving faster with reference to you, right? So the faster magnetization vector, which is a precision frequency faster than this, okay, and this is a slow vector which is a precision frequency slower than this, right? Assume this is positive and negative for symbolizing it. Doesn't really mean anything. It doesn't mean that it is a positive or negative in real sense. It is just for recognition. If at this stage, if you give them a 180x pulse, they will go exactly on the mirror image position. So this is your negative and this is your positive. Remember, positive is moving as it was, right? And the negative is moving as it was. The only difference is that in this case, they would merge and then split again. So they would merge after a certain time, and this is the time which you say this coherence to this coherence is an echo, right? Is an echo. What you have done that you have created a coherence again. The coherence which was lost is again created. Is again created. Now you can ask me a question, why you want to do it? It doesn't make sense. Huh? Well, I don't know why. Anyway, so it is coherent now signal, right? Again a question. It would again split because it doesn't have the same speed. It will again split into one which is slower moving and the other which is faster moving. If you give another, make it coherent here on Y, and you can keep doing it for 2-3 days. No? Till when? until it relaxes back to. So you can play it with only for a certain period of time. This coherence can only be created after for a certain period of time, right? Because relaxation is. Now question why you want to do it. Number one, that you have the capacity of creating the coherence again, and we would study a multiple coherence. We would study a whole class of experiment in which this innovation was used to create coherence again and again, right? This one. The second is that you have the capacity of controlling the chemical, isn't it? The chemical shift is, and then you again make them coherent to each other. Okay. So, for instance, if you want to record an NMR spectrum, and again a very confusing statement, everybody become very alert. If you want to have an experiment in which you want to make sure that there is no difference in chemical shift, what you would do? That the difference in chemical shift is minus from this system. You keep doing it. Spin echo experiment. Huh? Yes, it makes no sense, isn't it? And I'm not claiming that should make any sense. I'm just telling you that you are not observing this. You have nuclei on XY plane, on another nuclei in the XY plane, where this chemical shift difference of proton should not make any difference. For instance, carbon 13. You want to record only carbon 13 with absolutely no contribution of the long range coupling or a short range coupling of proton. So you keep doing it. Or you do it TOCSY, total correlation spectroscopy, in which everything in the spin system become absolutely on the same chemical shift, and you record only the coupling constant. So you can do it, Capacity of controlling the chemical shift difference. This is your capacity, right? And one more thing. For some period of time before you do something different. And you would understand that. Yeah, so as we move forward, you would understand why spin echo experiment. Okay. That this splitting of signal is not because of the chemical shift, but because of the magnetic inhomogeneity, an experimental error. Problem with your, because of the problem in your magnet, you see the same proton split it into two different signals. ये बात समझ में आती है कि why because of magnetic inhomogeneity same type of protons can give a different signal. Do you appreciate the fact? Yes. You do that, right? It's important because if we don't understand that, we will not be able to appreciate, right? Now this magnet, despite the fact that you have done lots of shimming and you have got a very good magnet, your magnet develop a problem called drifting. There is a problem called magnetic drifting. Superconducting magnets have an inherent bimari, a disease which is called drifting. And this drifting is a serious disease of magnets. During the NMR experiment, they drift because of multiple factors. Number one, they are aged. They have a niobium coil which has accumulated lots of niobium oxide. As a result, it's not a perfect magnet. And when there is oxidation, the surface is oxidized, the inside is not oxidized, drifting. Number two, liquid helium is not sufficiently available into the system. They have a drifting. Because of any factor, you have a magnetic inhomogeneity. How you will calculate? How will you make sure that your signal remain coherent and should not have any contribution of magnetic homogeneity? By this, isn't it? मेरी खुशी की खातिर ही कहते हैं. अरे मेरा ख्याल है कि मैं चाय पी के छोड़ के ना कुछ कॉफी किसने कहा आशीष. So magnetic inhomogeneity, the contribution of magnetic inhomogeneity can be nullified by using. Okay. I want to ask you a question also. Tell me, can we use it for the calculation of T2 time, big T2? What was the spin relaxation? Spin relaxation was a relaxation in which one spin transfer the energy to the another spin within a system. So if I say that these 2, 3, 4, 5, 6, 7, 22,000 different signals are transferring energy to each other, and if I tell you, please calculate average T2 for me, would you be able to do it? No. Fine, khatam hi ho gaya. We should go out. What is T2? What is spin relaxation time? Spin relaxation time is a time in which you see the maximum relaxation of your coherent signal splitting in coherent signal because of spin transfer of energy, right? Assume that you have, instead of 2, 3, 4, 5, 6, 7 different nuclei, and all of these nuclei are transferring energy to each other, right? And then they split to the maximum. You know, jitna split ho sakte hain, utna split ho gaye. They have split it to the maximum. And if I tell you that if I just take it from here to the here, I can calculate T2 by combining this T with this T, tau with this tau. I'm not claiming that the system is going anywhere. I'm just asking you that spin relaxation is a process. Spins split, give energy to one to the other. T2 here. Can I do it? Absolutely. Because split into several peaks, 1, 2, or 3, and it takes certain time. And when you give a 180 X pulse, then go to the negative side exactly on the mirror image position. Then they take some time to combine together. Then this is your T2 time. किन लोगों का एतराज है इस पर? I expect you to disagree with me because I want you to understand that. Okay. What is spin relaxation? Spin relaxation is not a true relaxation in which energy goes out of the system. It is a relaxation that really means that the spin within a system is transferring energy from one to the other, right? Coupling भी तो इसी जैसे होती है ना? That's how you do that. That transfer of energy, let's say in a methanol, in an ethanol, the energy of methyl CH2 and OH is transferred to the. There is a question.
Yes, sir. Sir, Assalamualaikum.
Walaikum salam.
Sir, I am Rizwana from Government University. I am MPhil student. Sir, I have a question that due to the non-homogeneity of magnetic field, the same proton give different signals. Why?
Okay, this is an important question, and I'm glad you asked me. Thank you so much. You see, kindly recall that the precision frequency of all the nuclear spin are directly proportional to the applied magnetic field. Right? And Rizwana, I expect you to say right. Rizwana, I'm waiting. Okay. So.
Tutta via Isha, okay.
Ji, sir.
Thank you so much. So, if your magnet is not stable, and if it is not really giving you the magnetic flux density uniformly, it means that it is non-homogeneous or heterogeneous magnet. So if you have, let's say, toluene in your sample tube, methyl and phenyl protons, this methyl and phenyl proton, this toluene, throughout this 5 mm tube, you have a sample tube, and this is in between the magnetic field. And if this magnetic field is not homogeneous, this toluene and phenyl protons are experiencing different B naught, slightly different B naught. And when they will experience different B naught, they would have a different precision frequency, which is so sad because methyl should appear as a singlet. But instead of appearing as a singlet, depending on the inhomogeneity, it can appear as 3 peaks, 4 peaks, 5 peaks. I'm not really using word doublet, triplet, or triplet because they are not doublet, triplet, or quartet. There are 3, 4, 5, 6 different ghost peaks because of magnetic inhomogeneity. B naught is not homogeneous, right? And always remember that this slight difference in precision frequency is your NMR spectrum. So you can't afford to have a magnetic inhomogeneity in your experiment. If you would have a magnetic inhomogeneity and if you start seeing several signals of a same toluene methyl, then you are in deep trouble. You would not be able to calculate anything. This is the wrong NMR spectrum. No concept of chemical shift, no concept of coupling would appear out of this lousy, bekar, fuzul NMR spectrum, right? Because of magnetic inhomogeneity. So in order to, this is one of many applications of spin echo, that by giving an echo pulse, which is 180x pulse, remember, 180x pulse. Wherever you see in NMR experiment, in between two gaps, in between two delays, a 180x pulse, this is always a spin echo pulse. So when you give a 180x pulse, you bring them on the other side of the X5 plane, like you have brought them from here to here, and they combine together. So what you have done, you have nullified the effect of magnetic inhomogeneity. Okay? Question again, yes. Yeah, that is the flexibility of NMR spectroscopy, that there are lots of things which you wanted to do with the hardware, now you can do it with the software. Remember, there was a time in 60s and 70s where the only solution of the problem of sensitivity was designing large magnets, right? In order to increase the signal to noise ratio, buy a large magnet, right? Because large magnet, large population difference, large signal, right? But then people said, why can't we do it in a different way? Why can't we do it in a non-hardware dependent manner? Why can't we have a pulse Fourier transformation? Why can't we lump them together, record FID, and we do lots of experiments, and then we combine them together, improve the signal to noise ratio, increase the sensitivity, right? And the same fellow, we must really get another Nobel Prize by discovering the polarization transfer. But Richard Ernst discovered the polarization transfer. Another way of increasing the sensitivity, which we will discuss maybe day after tomorrow or so. Okay, so shimming is a manual process which people do on their NMR machine in order to have a homogeneous magnetic field. There is a heterogeneity in magnetic field, and you want to compensate by using magnetic wiring, increasing, decreasing at different sites, Z gradient, X, Y, Z. You do lots of these X, Y, Z shimming. And you try to have a homogeneous magnetic field. But of course, you may still have a magnetic inhomogeneity because of multiple effects. Drifting is a problem which cannot be corrected by shimming. Shimming is a very, very minute, very sophisticated process which can only handle small differences in magnetic field. But you have a drifting from 300.1 to 298, then you are in deep trouble. In that case, you would have 2, 3, 4, 5 signals of the same photon. In that case, spin echo is actually used to save you from the impact of magnetic field inhomogeneity. Now, my question is, can I use this particular technique, spin echo, in slightly different manner to calculate the big T2 spin relaxation? This was my question. And this is question related to what Dr. Humera asked me, that this particular type of experiment, so-called spin echo experiment, has okay, so you can use it for calculation of big T2, right? Okay, I want to ask you a question. I want you to design an NMR experiment for me which can calculate T2. And let me tell you what T2 is. T2 is the time in which maximum energy is transformed from one spin to the other spin. Okay. So if it is taking, for example, these are 5 peaks, and they all are coherent. And if it is split into 5 different peaks, maximum 5 different peaks, with maximum transfer of energy, the time it takes from this to this is T2. How you will calculate that for me? How you would measure it for me? I want to tell you the solution. The time it takes to split, and after the 180 expulse, time it takes to merge together is T2 time. Confirmation over here. When it's split, you're not measuring it. You just know that it is taking so much time. But when you do 180 expulse and wait for a while, when you see an absolutely coherent negative Y signal, you say this is the T2 time. Yes? God, I see some shining faces. Not so many, but anyway. Uh, T2 time. No, this is for measuring it. This is not for. Remember, this T2, this 180x pulse is a pulse which bring everything on a mirror image position, and you wait. You turn on your detector and you wait for a while. You would eventually have a time when your detector record one coherent big signal, and that one big coherent signal from the time of 180x pulse to the appearance of a one big coherent signal is your T2 time, because that is exactly similar to it takes to split. It take exactly same time to combine together. Always remember this tau should be exactly similar. They're confirmatory test. So you can calculate the big T2 time by using spin echo experiment. But honestly, I don't understand why you would like to calculate T2 time. मुझे मेरा दिल नहीं मानता इस पे, पता नहीं क्यों. Okay, but you in NMR, you becoming an NMR spectroscopist. You're transforming from a normal human being to normal NMR spectroscopist, right? So this transformation required you to understand all these T1 and T2s of different types. Okay, you remember this? 180 pulses, and whenever you give 180 pulses, you see a coherent signal again, right? And eventually they disappear because of a simple reason that they are relaxing back. So these are T2 times, isn't it? Between them is a T2 time. From a fully positive signal to a fully negative signal, the time it takes is your T2 time. And you calculate it, you cannot calculate it without a 180x pulse. You cannot. Do that. Okay, this was the, now, this is the one, मुझे थोड़ा इसको एंजॉय करने दो. ये क्या हुआ है? 180x पास दिया है ना? And then why is going? Oh god, this is beautiful. I can see it for several hours. ये क्या है? ये क्या है? फर्स्ट ऑफ ये क्या है? ये क्या है? और दोनों मिला के क्या है? गुड, शाबाश. कुछ कहने सुनने की जरूरत ही नहीं रहती. अब बताइए सरोज, आप क्या पूछे थे? रिलैक्सेशन टाइम देना है हमने. नहीं, आप रैंडमली सेलेक्ट करते हैं. You see, you eventually decide when you see a positive to 100% positive coherent signal to 100% negative coherent signal. that tau is defined by a several experiment. You vary it, and eventually you reach to a stage where you would see that from a positive signal splitting n to the negative signal when it goes coherence, this is an optimum tau time which is called t1, t2. So you calculate. So you vary this tau time from 1 second, 2 second, 3 second, 4 second, 5 second. You eventually reach to the maximum time when it is split, and that exactly the same time when it. Okay. Let me ask you a question. If it is split to a level when it goes to this side, अगर आपने इतना टाइम दे दिया इसको, बस ठीक है. एक आपकी, just for our own understanding, assume that this time you have given was so much that this has split it to a level when it goes to this side and this side, right? Huh? Then 180x pulse will bring it where? राइट हैंड अपना निकाले, सब लोग अपने राइट हैंड निकाले. सॉरी वो आपका लेफ्ट है, राइट ही होता है, ये वाला होता है. जो इस वॉल की तरफ है ना वो राइट होता है. So you right hand, right? This is the direction and this is your magnetization vector. It turns like this. Mirror image. If you give an extraordinarily large delay, then they would go onto the other side of the XY plane, and in that particular case, you would never get an echo. You would never get an echo. You would get a positive signal, so you would never know what is the actual time required. So you slowly optimize this time unless you get an echo, right? This is the T2 time calculation. इतना अच्छा है कि इसको बार बार देखने को मिलता है. Give me a break also. Okay? Please see that it is not really going to the other side. Just giving it a time, and this is 180x pulse. This is echo. So between this time to this time is. You're not turning on the detector at this time. You're turning on the. You turn. Absolutely. You give a 180x pulse, then you turn on the detector, and then you turn on the detector in different interval unless you see a full positive, full negative grown signal, coherent, absolutely coherent. This is T2 time. This is. So this is a technique through which you can calculate the T2 spin. What is the advantage of calculating T2? I don't know. There are lots of advantages. There are many experiments called mixing time. NOE में भी होता है बहुत सारा mixing time. T2 is big T2 is an important term when you talk about a slow relaxing nuclei. So people use T2 now to calculate how much energy is transformed from one spin to the other and how long it takes. So T2 is actually used in many experiments, particularly so-called mixing time experiments. Anyway, let's move forward and now I want to take you I, uh, I will take you from laboratory frame of reference to the rotating frame of reference. Until now, at, at this particular time, you are in a laboratory frame of reference. You are watching the events happening on xy plane on this Cartesian coefficient on these three angle coefficient, three axes from outside. You are not part of the system. And if I tell you that you would never be able to understand this whole concept if you know that they are actually moving with the velocity of radio frequency, all of them 300 megahertz के हिसाब से सारे move कर रहे हैं. This X and A, don't worry about static. You see, all of them are either slower or faster. They are moving with the frequency of applied radio frequency, with only slight tiny difference. All of them. So imagine around the axis of the B naught, which is ever present, right? So on xy plane, all of these magnetization vector, splitted magnetization vector or spins are moving with the speed of radio frequency. All of them moving so fast. Would you ever be able to appreciate the fact that which one is slower and which one is faster? Be in a laboratory frame of reference. You would never be able to see. You would never be able to see which one is faster and which one is slower. And there are lots of examples. Most interesting example is the example of merry-go-round. ये जो वो नहीं होता, क्या कहते हैं इसमें, ये अक्सर गांव वगैरह में होता है, नॉर्थ वॉल की साइड में इस तरह होता है वो. In melas, you have in festivals, you have these merry-go-round. Merry-go-round, you have different animals, the statues of different animals, right? Any question, please? Okay, so when you have this particular platform in which we have a horse, a lion, or different things, and you see different children sitting on them, and it's moving extremely fast, you would not be able to see the exact happening on this particular platform, right? But if you jump over it, you would be able to see everyone so clearly. If I tell you that these two are moving with the radio frequency velocity of 300 megahertz or 600 megahertz or 800 megahertz, and if you jump on one of them, you become the part of a needle, just stand on a needle, then you would be able to see which one is moving forward and which one is lagging behind, right? And this moving forward and lagging behind is because of the precessional frequency differences, right? The differences in precession frequency is generally in hertz or maximum in kilohertz, for instance in carbon 13. But the velocity, the frequency of these magnetic vectors is several megahertz, 300 megahertz, 400 megahertz, 600 megahertz. Assume that this is moving with the speed of 299.9 megahertz, and it is moving with the speed of 300.01 megahertz. You would never be able to see the differential frequencies of two of them unless you become the part of the system. So if you want to understand what is happening on xy plane, you have to understand the whole sequence of the whole everything as a part of the process, and it's called rotating frame of reference. Rotating frame of reference can be absolutely misunderstood by assuming that this XY plane is rotating with the magnetic field of MA. Therefore, MA becomes static, right? MA becomes static and only MX is moving forward, right? The difference in frequency of this, the differential frequency, is your chemical shift. Or it can be TMS. The frequency of TMS becomes the frequency of rotating frame, right? And everything which is different from TMS is either moving forward or lagging behind in certain cases also. And then you would be able to appreciate the differential frequency. Practically, how can you do that? Very easily. If it is 300 megahertz NMR machine, you just minus 300 megahertz. When you minus 300 megahertz, you see only 0 point some megahertz on one direction and 0 point some hertz in positive direction. So in order to visualize the event on an XY plane, you need to understand the concept of a rotating frame of reference, because this absolutely mind-boggling motions. No one of you has actually asked me that why you're treating NMR spectroscopy in such an oversimplified version. Why you say that it is split into 2 or 3 or 4 or 5 or 6. How can we see it? We cannot see it. Because they all are moving with the speed of radio frequency. And when they all are moving with the speed of radio frequency, you would never be able to say which one is the faster moving and which one is the slower moving. Your case of predictability fail in a laboratory frame of reference. I want to say that I want to give a pulse to the system when mx is on x. Okay? Will I ever be able to see this mx on x in a laboratory frame of reference? I would never be able to see. I would never be able to see it because this is moving with an absolutely mind-boggling speed around the axis of ever-present B naught. ऐसे ही है ना? And at the same time relaxing, losing the tip angle, going back to the Z. So there are lots of things happening which would never make you understand the process, which is moving forward, which is moving backward, when they will be on X, when they will be on Y, when they will be on in between X and Y. You would never be able to understand until we develop a concept of rotating frame of reference. And rotating frame of reference is a very, very simple concept. It is a concept in which you take several spin, one of the several spin as a static spin with no difference, and then you see everything with reference to that static, right? So for example, this MA, there are two protons, two types of proton. One is MA and the other is MX, and you selected MA is the frequency of your rotating frame. So mx is moving forward to this, right? And the difference between them is your chemical shift. Now, this definition is substantially different from a normal definition of a chemical shift. But it is essentially the same at a conceptual level. What is different is precision frequency. And why precision frequency making it moving faster? Because of the electronic environment. Therefore, essentially the concept is same, but in rotating frame of reference, the chemical shift is understood with reference to its movement from a reference rotating frame of static magnetic field, and you see it moving forward. In case if you have a three different protons and the other is lagging behind, this would move to this direction, right? And this would move to the other direction. Now, in this rotating frame of reference, you would be able to see one moving to this side and the other moving to this side with what frequencies? In megahertz or kilohertz or hertz? In hertz, right? Because this is a differential frequency. Two cars running on a road, when they move differently from each other, this is only the difference in frequency which make them apart from each other, not the speed. The speed has already been minus. The average speed has already been the minus. The only thing which makes difference is the difference in velocity, difference in the speed of two cars, right? Or three trains or four, five, or whatever you just, whatever vehicle you like or plane, huh? But that is the rotating frame of reference. Professor Tarman gives this example of a watch, clock. These are three different spins, split because of their precession frequency. Which one is the slowest moving spin? And which one is the faster moving spin? Second. And if they are just moving very, very fast, you would not be able to understand. But if you jump over on one of them, you would be able to see the difference in velocity of angular velocity of three different needles, right? This is the rotating frame of reference. कोई शक? Yes. प्लेन की एग्जांपल दे दें. अच्छा, फैन की. Why you think that you really need to jump? You know, everybody's so scared. Jumping on a magnetic field which is moving with the speed of light, you know, radio frequency is the light also, scaring everyone. You don't need to do it. You just assume. हाँ, plane आपको पसंद है? Fan. I don't like fan anymore, you know, because fan, all three spins of fan or four spins of fan, they are moving with the exactly same direction. Eh? And so it's not a good example, right? Merry-go-round, eh? उसको उर्दू में कहते क्या है मुझे आज तक समझ नहीं आया. यार उसको जिसपे गधे घोड़े बने होते हैं जिसके ऊपर लोग बैठते हैं. झूला नहीं है, झूला. Somebody from outside, can you tell us what is the name of Urdu name of merry-go-round? आपकी तरफ तो बहुत होता है ना.
सर लट्टू नहीं कहते.
क्या कहते हैं?
लट्टू
कहते हैं. आप उसको कहने को तो कुछ भी कह सकते हैं, मगर ये वो मैं उसकी बात कर रहा हूँ नहीं, वो जो एक झूला होता है ना. सॉरी फॉर you know I'm using Urdu word. It's not important. It's not anima. It is more of play and fair. ये जो एक गोल सा होता है जो घूम रहा होता है जिसके ऊपर बहुत सारे जानवर बने होते हैं और उसमें आप अपना बच्चा बिठा देते हैं और वो फिर तेजी के साथ मूव कर रहा होता है और आप खुश होते हैं कि आप अपने बच्चे को हाथ हिला रहे हैं जबकि आप किसी और के बच्चे को हाथ हिला रहे हैं, बिकॉज इट इज ऑन अ वेरी फास्ट मूवमेंट, राइट? क्या कहते हैं इसको? Yeah, I don't want to waste time. बस कुछ ना कुछ कहते हैं. But this is called merry-go-round, and it's a good example that when you jump over it, then you would be able to see everything with reference to your own frequency because you are moving with the same frequency, right? And this is your rotating frame of reference. Why it is important? It is really important because of two purposes. Number one, that you don't want to use this useless large frequency which is common in two spin. Because if you record that useless common frequency, your detector would be overwhelmed. And what I mean by this, you see, what is of interest to you is the difference in the frequency of these two rather than their own frequency as a whole, isn't it? The chemical shift is measured, the chemical shift, the difference in precession frequency is only in hertz, while their movement it is in megahertz, right? Megahertz, if you want to record the whole megahertz, then your detector would be overwhelmed. So detector has a capacity of minusing the average frequency out of the system. So your calculation is not done on 299.9 megahertz or 300.01 megahertz. Your calculation is done only on few hertz. So the FID has a mechanism of minusing the reference frequency. Make life so easy because calculation become easier, right? Number two, in order to understand the NMR spectroscopy, the predictability of NMR spectroscopy is based on your understanding that where your magnetization vector would be, isn't it? And you cannot understand the position of the magnetization vector in laboratory frame of reference. You would never be able to understand. The only way of you to understand where your magnetic vector would be when you have a rotating frame of reference. Okay? So rotating frame of reference has a wonderful connotation. It has lots of advantages in order to understand the predictability of magnetization and NMR spectroscopy. Now, any rotating frame of reference is in the rotating frame of reference you use any signal as a you can use as a TMS also if you wish to. Otherwise, if you are not using that one, then it doesn't matter. You can have a solvent signal as your reference frequency and anything else also as a reference frequency, right? And when you have a reference frequency, that means that you are actually minusing the reference frequency with the differential frequency. So the differential frequency, not the position, please try to understand, is the differential frequency between these two signals is the chemical shift. Chemical shift. It doesn't really mean that when mx will go here, the difference between these two would increase. No. Because this is an average. This is only the differential frequency. Now, at this point of time, we understand that the chemical shift in rotating frame of reference is substantially different from the initial concept, although the reason is exactly the same. Reason is same. Okay? Yes, please. How you select that? Yes, you don't need to worry about this very much because you see a reference frequency, for instance, if it is proton NMR spectroscopy and if it is 300 megahertz NMR instrument, remember 300 megahertz NMR instrument is the average radio frequency, average precision frequencies of all the protons. Some of them are less, some of them more. So if you use 300 megahertz as your reference frequency, you don't need to worry about it because some would be moving less and some moving faster, and that become your reference frequency. So you can have a compound peak, you can have a TMS peak, or you can have just a frequency as a reference to minus it from it in order to see the events on XY plane much more clearly and not overwhelming your detector with lots of useless frequencies which you don't want to, which doesn't make any difference to you. Okay? यही होता है ना chemical shift में, when you average out chemical shift, you just average out the megahertz. Megahertz is common in both of them. The only difference is in hertz, right? That is your chemical shift. So this is the, now what is difference in coupling constant? Coupling constant is nothing so extremely different. You see, for example, in this case, this is a doublet. Huh? And doublet primarily means that we can say J half here and J half here. This is the difference in frequencies of the two peaks of a doublet. Tick. One is moving slower and the other is moving faster, and therefore they appear as a doublet. Okay, and they can move to that stage where they are, one is on minus x minus, they move on it also, differential frequencies. Let me ask you a question, a basic fundamental question. Why one component, let's say methyl next to a CH, why methyl protons appear as a doublet when they are next to a CH? Which doublet means two peaks, right? And these two peaks means that one is slower and the other is, that's why they are appearing in two different peaks, right? So this splitting of one signal of methyl is because of some reason. And this reason is independent of its own electronic environment, because electronic environment is chemical shift. But when they split into two parts, why a methyl next to a CH is split into two signals? Any other explanation? Okay, this is a good definition, but why it is split into doublet? Why not in triplet? Why not in quartet? Why not in next? Can it be in terms of nuclear spin rather than electron? CH next to a methyl. Remember methyl. Methyl yaad rakhe. And then you go to a CH which is next to a methyl. This CH proton can exist in two different possibilities, in two different states. One is aligned to the magnetic field, plus half, and the other is, when it is aligned to the magnetic field, it reinforces the magnetic field. And when it is opposed to the magnetic field, it is cancelling the magnetic field. So when it is aligned to the magnetic field, it is adding to B naught. And when it is opposing to the magnetic field, it is subtracting from the B naught. So methyl would experience two B naughts, right? One with addition, the other with subtraction. And therefore it would have two different precision frequencies. When it would have two different precision frequencies, it would appear as a doublet. Agree? Classical definition in a different context. Classical definition. We're talking about now precision frequencies. In our undergraduate text, we don't learn about precision frequencies. It is only learn that if it is beta, beta, alpha, beta, 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 alpha beta. Alpha beta. Huh? ये पक्का हो गया? Is it पक्का now? Okay, if you have a CH2 next to a methyl, then why methyl appear is a triplet? Three possible arrangement of neighboring nuclei. Two CH2s can be both alpha or both beta or alpha beta, beta alpha, right? And therefore, the magnetic field felt by methyl is different from pure B naught because of adding and opposing effects, right? So it appears as a triplet. I want to ask you $1 million question, and if you can respond to this, you can have $1 million, you can pray from Allah, and Allah will give you $1 million. Question. If I give a 180x pulse to this system, remember spin echo, right? Will I would be ever able to develop an echo? जो नहीं कह रहे हैं ना वो बता दें, $1 million उनको अल्लाह पाक जरूर देंगे. Will I ever be able to develop an echo in this case? This is slow moving and this is faster moving. It will go here and it will go here exactly on the mirror image position. Will they be merged? Of course. No, of course not. लोग दो हिस्सों में जवाब देते हैं, of course, and this is of course not. So, will they ever be able to merge? Yes or no? Why no? Huh? Change in spin level. Change in spin level. Remember, it is split it into two because it has a CH next to it, a one proton. When you give a 180 pulse, the alpha become beta and beta become alpha. So this was watching BVA. B was watching alpha. When I give a 180x pulse, this would watch alpha and this would watch. This spin relabeling will never let them merge. Now you understand that spin echo can only create coherence in case of chemical shift, not in coupling constant. Very exciting. Huh? नहीं आया समझ. So it doesn't matter. ऐसा होता है. Okay. First of all, let me ask you a question. Why it is slow moving? Why it has a precisional frequency? And remember that it has a CH next to it, जिसको अभी हम देख नहीं रहे. We are not really watching CH signal. We're just assuming that it has a CH signal, CH next to it, right? And this particular part of the magnetic field is watching C1 in opposing direction. Therefore, precision frequency is slightly less, right? And this particular part of the nuclear spin is watching CH into alpha, right? That's why alpha is the aligned magnetic field. As a result, this is the addition to B naught and this is subtraction to the B naught. This is very well, it is moving away from each other. One is slower, the other is faster. question is, if I give 180x pulse to all Harjans, what will happen? This CH, remember the CH, ab isko bhul jaye, just forget this. This CH, because of which you are actually seeing this magnetic field, was alpha and beta. When you give a 180x pulse, they would switch. Right? Alpha become beta and beta become alpha. So this which was coupled with the beta part of the CH will now become alpha part of the CH. And this which was coupled with the alpha part of the CH, and they change the direction. And when they change the direction like this, going faster. This slower moving become faster moving, and this faster moving become. And when you would have a situation like this, they would never merge on Y plane. They would remain away from each other and slowly go away from each other. Because of a simple fact that this 180 Harjan pulse is affecting all the protons in the system, including CH, which is splitting your signal. And the CH, which was, some of them were alpha and some of them were beta, which were splitting these two, would become, and it's called spin relabeling. So as soon as the alpha become beta and beta become alpha, this would have a relabeled. Initially they were with the beta, now they are with alpha because their neighbor has switched the label. And this was with the alpha and they become with the beta. So slower moving become faster moving and faster moving because of this slow moving. This only happens in a homonuclear system. Please try to understand. Because 180x pulse, 180 pulse is non-distinguishable. It relabel all the protons of the system. And when it relabels CH also, which is a neighbor of it, then you see a constant relabeling from negative J half, it become a positive J half, and this become negative J half. And as a result, when you do a 180x pulse, they would not merge together, but they continue to move away from each other, because this splitting is because of the contribution of the neighboring proton, neighboring nuclei. So the spin echo experiment can only handle the chemical shift, not the coupling constant. Oh God. हाँ कहने के हो जाएंगे, जिंदगी में बहुत सारे ऐसे वक्त आते हैं जो बहुत सारे लोग कहीं ना कहीं reunited. You're absolutely right. But 180x pulse would not really reunite. 180x pulse will not create an echo in it. 180x pulse would not create a coherence into this. 180x pulse will continue to grow them in a different direction, because in the case of chemical shift, they were just mirror image and they merged together. In this case, they got to the mirror image and at the same time they relabeled. Neighboring CH is now alpha to beta. I mean, assume that you have a rich neighbor, right? And every day he's sending lots of food and gifts to your home. So you're influenced positively from him, right? Neighbor? look at the contribution of frame of reference. If it is not the frame of reference, then we should not really be seeing them moving apart. The reason why we are seeing them is because of the simple fact that you are in a rotating frame of reference. Okay, because that's how. Now, assume that you have a neighbor. I like this neighbor example. Okay, and suddenly this neighbor become very poor. And he said, yeah, you start sending me food and gift now. इसमें कोई खास मजा नहीं आया because relabeling वाला concept नहीं आया. Positive enforcement and negative enforcement वाला तो आगे है. But anyway, please remember that 180x pulse relabel CH. CH which was alpha become beta and beta become. As a result, these two components are now coupled to a very different peak. This was coupled to beta CH and this was coupled to alpha CH. After 180x pulse, this is coupled to alpha CH and this is coupled to beta CH. As a result, faster moving becomes slower moving and the slower moving become faster moving, and when they go there, they go. And when they go there, they move this direction and this move this direction. They would never have a coherence. Thoda sa, after having evening tea, you think over it, and I'm pretty confident that you would be able to understand. Precision frequency of these two halves of the same nuclei is dependent on the nuclear orientation of the neighboring proton. This is coupled to a CH, and this H exists as alpha and beta. The slower precision frequency is because of its coupling with the beta, the opposing one. And the faster precision frequency is because of its coupling with the alpha. ये समझ में आता है? नहीं, ये तो आप तय कर ले. Why one is moving forward faster and the other is moving slower? Why? And when one is aligned, then it is ending into the B naught. And when it is adding to the B naught, the precision frequency is directly proportional to the B naught added, right? And the one which is opposing is B naught subtracted. And the precision frequency is directly proportional to the B naught subtracted. As a result, it would have slightly less frequency, precision frequency. The other would have more frequency, precision frequency. Now the question is, if you change the partner, this slower moving become faster moving, and the faster moving. And how can you do that? By relabeling. This is your CH. Assume that this is your CH, this is alpha and this is beta. When you relabel them, the one which was coupled with the alpha is now coupled with the beta, and the one which was coupled with the alpha is coupled with the beta. As a result, the slow moving become faster moving, and the faster moving become and slow moving. So when you would make a diagram, I want you to kindly make the diagram. You just make a diagram at mirror image position and just change the direction. And when you change the direction, it is no more like this. It is like this. And this one is no more like this. It is. As a result, they would continue to split. They would never reunite. As a result of 180x pulse. What I'm trying to say, it has a lots of importance, because NMR experiments, you play with it. In NMR experiment, sometimes you just don't want to see the contribution of chemical shift. And in that case, you bring them together, but coupling constant continue to split. 180 X pulse cannot nullify the coupling constant difference. 180 X pulse can only make chemical shift coherent. Okay, so you use these pulses and properties for the benefit of your understanding, for designing the pulse sequences in which you play with them. Okay, Yasin is laughing at. Okay, any question? It's difficult to digest, huh? Let's start all over again from first slide. The title page. Right? Okay, from here. Let's go to more complicated. Sometimes more complicated things make you understand. Yeah, I'm sorry, I don't want to go into it. It's too risky. Okay. This doublet is because of what? सबसे पहले तो मुझे why this assume कर लें methyl है चले ठीक है methyl is appearing as a doublet. Why? When methyl appear as a doublet? Next to CH, right? And the CH में एक प्रोटॉन है, right? और ये जो प्रोटॉन है ये भी प्रोटॉन है, ठीक है? Or this would also have an influence of magnetic field also. It can also align and oppose. So your methyl see it in two different ways, align and oppose. Those methyl which see it align move faster, and those methyl which see it opposing move slower. ये clear है? ये भी clear नहीं है, कोई बात नहीं. Yes, thank you so much. ये methyl को आप भूल जाएं. Methyl is just methyl, one big globe, you know. And this methyl is next to a CH, right? And they all are experiencing B naught, right? The CH is not visible into your system for simplicity. You don't want to see CH at the same time when you see CH3, otherwise you would see a quartet which will make life much difficult, right? So you just CH, you remember CH, याद रखें इसको अपने ज़हन में रखें, ठीक है? And the CH, this H is either alpha aligned to the magnetic field or beta opposed to the magnetic field. In those cases in which it is aligned, it is adding into the magnetic field because the direction of its own magnetic field, which is a vector, is adding to the large vector of the V naught, right? As a result, those methyl which are seeing the CH in alpha direction are experiencing more magnetic field. The B naught, B effective is more than the B naught, right? Because you have an adding effect. Okay. Those unfortunate methyls which are watching the neighboring CH in opposing direction are experiencing less than B naught because the negative vector of of the CH is on the opposing direction of the B naught. As a result, the B naught is slightly less for them. As a result, they are experiencing slightly less B naught, right? And as a result, they would have different precision frequencies. And as a result, they split into two parts. The one with, this is the one with alpha CH, right? Alpha H, alpha neighboring H. And this is with the beta neighboring H. And why they are moving this direction is not because they are moving this direction, they are just lagging behind in a rotating frame of reference. It is moving all in the same direction, but this is moving slightly slow and this is moving slightly faster. Therefore, you see this thing moving like this and you see this thing moving in lagging behind her. It is not the direction of the movement. Now, this negative and this positive is showing the sign that this is the large precision frequency because of alpha neighbor, and this is the negative frequency because of beta neighbor. If you can somehow make alpha into beta and beta into alpha, what will happen? This negative become positive and this positive become negative. So this faster moving will become slower moving and this slower moving become, and you have done it by using 180 axpal. So when you take them on the other side, they would continue to diverge and they would never reunite, right? और मैंने आज तक इसका इतना इस्तेमाल कभी नहीं किया. This depends on diagonal angle. And the diagonal angle is a scalar quantity. Is a scalar quantity because this, remember, there is no direct transfer. I don't want to confuse you. There is no direct transfer of the nucleus spin from neighbor to neighbor. It is always through electrons. Therefore, it's called scalar coupling. Therefore, it's scalar coupling. Remember, when you have a diagonal angle, you have a different orientation of electron. We'll go into it, but we'll not go to a level when I confuse you to the limit. Diagonal angle is an angle on which these J values are dependent, and these J values are dependent because of the orientation of the neighboring proton. And this neighboring proton की orientation है, that is transferred to methyl, for example, CH से methyl पे transfer होती है. Impact is seen through electron, goes through electron. But please, अभी इसके ऊपर मत जाएं, बहुत problem होगी. Okay, just is it okay that spin echo converge chemical shift differences and spin echo cannot converge the chemical shift difference? Because, yes, because of the relabeling of neighboring protons. This is a very important concept because this concept is the basis of toxic correlation spectroscopy. Total correlation spectroscopy or HO-HA-HA, right? Homonuclear Hartmann-Hahn spectroscopy is based on this fundamental concept that you can bring all the wavelengths of the same spin system with exactly identical chemical shift by doing spin echo, train of spin echo constantly, while the coupling remain divergent. Very important concept. Very, very important concept. Okay. tomorrow. 1:45 please. नहीं कल अनाउंस हो गया कल हो गया अनाउंस actually there was a problem my mother was going through but she's now rescheduled for the next week because her medication need to be changed so I would be online inshallah tomorrow exactly at 1:45 if there is any confusion kindly note that I would be delivering a discussion tomorrow at 1:45 and then on Wednesday. The reason why I want to take off for tomorrow is no more there. Next week I would probably have to take a day off on duty. Any question from the remote location from Gomal Sargodha University? Please feel free. I still have. And kindly note that you can also email me your question and you can also call me at any time. Anytime, yes, sure, of course. And I promise that we would really enjoy learning NMR spectroscopy. We faster than the average speed of. Assalamu alaikum wa rahmatullahi wa barakatuh. Thank you.